Welcome back to ECE 441A. This segment is going to talk about a particular root locus example, and really it's going to look at two different transfer functions, and we are trying to understand this question: which root locus pattern is it? There might be a couple of different possibilities based on the relative spacings of the poles and zeros, and we want to determine which particular pattern is it going to be, or is there a way that we can determine which pattern it is. And in fact, we will find that this is utilizing rule number 4. This is really an illustration of how one can use the concept of the relative minimum and the relative maximum of the magnitude of our gain k, which is really coming to us from the magnitude condition, to determine the root locus pattern or the structure of the root locus. What am I referring to? Here are two different patterns for poles and zeros that look the same. It's just that their relative spacings might be a little different, but you could have pattern number A, or root locus diagram A, or you might have root locus diagram B. They both have 3 poles and 1 zero. All the poles and zeros are ordered in the same way in terms of right to left on the complex S-plane. How do you determine whether you have pattern A or pattern B? That's what I want to try to illustrate in this discussion or in this particular segment. What it cannot be, a pattern it will not be, is pattern C. This pattern is not going to present itself. So that one's not possible. Don't be drawing something like this and saying, oh, here's my root locus. It's not going to be that squirrely. Why? Because the root locus branches in this pattern cross each other. That says, oh, there's an error there. And, or, the root locus pattern, if you start looking at it and following the branches around, you actually have inconsistency in the sense of the patterns or the branches don't make sense relative to how do 2 branches come together and produce only 1 branch coming away. So that's another source of error. What I want to do now is illustrate how we can determine which pattern we have, pattern number A or letter A or pattern letter B, and I'll do that with a couple of different transfer functions. Suppose that we now are tasked with sketching the root locus of g sub 1 of s. We have a numerator polynomial over a denominator polynomial. We have 3 poles and 1 zero. I'm going to sort of walk through the different rules, and I'm going to do it fairly linearly in terms of the fashion. You wouldn't need to do this, or you probably won't want to do this in real life or in an exam or on a homework, but I'm going to do these rules individually. Here's rule number 1. First, we need to identify the zeros and the poles. We only have 1 zero. Our poles that we are concerned with are at the origin. We have one in the right half plane, and we have another one in the left half plane. That's rule number 1. We now know where our poles and zeros are. We now want to do rule number 2, which is to sketch those poles and zeros and identify the segments of the real line that now possess or are a part of or belong to the root locus. Hopefully I've drawn enough tick marks. There's the pole at 2, a pole at the origin, a 0 at -1, and 2, 3, another pole at -10. With those locations now identified in the complex S-plane, we can now slice up our bread. We know that we have a segment of the real axis, or the real line, between the origin and +2, because there's one pole to the right of that line segment. We also have another line segment to the left, or in between -1 and -10, because there's always 3 poles and zeros to the right of that segment. We've now completed 2 of our rules in sketching the root locus. We now can see that something is going to happen off the real line, because we actually have a pole 0 excess that's more than just 1. We have 3 poles and 1 0. Our pole 0 excess is now 2, and that means that rule number 3 is actually going to be important. The pole 0 excess, or P minus Z, is 3 minus 1, or 2. So that is our pole 0 excess, which is a critical number that is used a lot in rule number 3. We can determine the angles of our asymptotes. Rule 3 is concerned with the asymptotes and how our root locus will behave for 4 large values of gain k. We have 180 degrees minus the pole 0 excess, and then that is times 2L plus 1, where L is going to range between 0, 1, up to P minus C minus 1. In this case, it only ranges up to 1. Our angles are now 90 degrees, which is 180 divided by 2, and 90 times 3, or 270 degrees, which really, another way we could write that is our asymptote angles are now at plus and minus 90 degrees. It's important for this case to locate the centroid of those angles, the asymptotic angles. Sigma sub A is now the sum of our poles. We had a pole at +2, we had a pole at the origin, and we had another pole at -10. And we then had a 0 at -1. We subtract the zeros algebraically, and we divide by the pole 0 excess. We now have -8 plus 1 over 2, or -7 over 2, or -3.5 for our asymptote location, or the centroid. Now let's, as I said before, typically you would just go back and put this on the pole 0 pattern that you've already created, but I'm going to do this in steps so that it's clear what's happening when. Here are now our poles and zeros. If I now put another pole at -10, and I'm going to simply guess at that location being sigma sub A, which is our -3.5, and let me go ahead and make that where I move away from that with my asymptotes. Here's my phi sub A equaling 90 degrees. Here's my phi sub A equaling 270, or -90 degrees. I have my third pole at -10. I have a segment there, and I have another segment there of my root locus. And now I know where my root locus approaches as k gets bigger. So 2 branches are going to go towards those dashed lines that are indicated now in that particular diagram. So this is now giving us this particular piece as just, again, a guideline, but the root locus approaches this or the root locus approaches these asymptotes as k gets large. And right now I'm not even going to sketch those branches yet that somehow start approaching those asymptotes for large values of gain k. I can indicate that my root locus branches will behave in these directions on that real line segment. I now want to get to the next rule, which is going to tell me where I'm going to break away and re-enter along the real line where I do have root locus segments. And that's now rule number 4. This concerns the breakaway and re-entry points. Again, if you were just doing this on the back of an envelope, you might not know which pattern you have, and you could potentially have a couple of different scenarios, as I've already indicated. You might have something where your root locus now is behaving such that the two branches in the right half plane meet between 0 and 2, and then when they meet they go off axis and they approach the asymptotes, and the open loop pole at -10 simply migrates into the 0 at -1, and it just continues to go in that direction. Another possibility would be to actually have the two branches between 0 and 2 meet somewhere between 0 and 2, break away. They actually then would re-enter the real line. One would go towards the 0 at -1, the other one would move away to the left of the breakaway and actually meet up with the pole that's coming towards the origin or the imaginary axis. Those would then meet and branch off and approach the asymptotes that are at plus and minus 90 degrees. What we need to determine is which pattern do we have. If you look at that, both of these patterns behave the same between the origin and +2. Both, and here I'm meaning both patterns, have a breakaway point between s equals 0 and s equal +2. How do they differ? Well, there are differences. One is the root locus pattern on the left has a k value that actually just monotonically increases. By that I mean there's no relative minimums or relative maximums between -10 and -1. K just continues to increase monotonically. So it's monotonically increasing the gain K. So the root locus pattern on the left has K monotonically increasing as the root locus moves from s equal minus 10, or the closed loop pole moves from s equal minus 10 as the, let me just say, as the, getting a little bit sloppy maybe with my terminology, as the closed loop pole moves from s equal minus 10 towards s equal minus 1. That's the pattern on the left. The pattern on the right has a slightly different behavior relative to how k varies between minus 10 and s equal minus 1. The root locus pattern on the right, if you think about it, it has a relative minimum as you enter the real axis, as you're leaving the two branches on in the right half plane, they break away and they actually return to the real axis a little bit to the left of s equal minus 1. That's then a relative minimum of k. So it has a relative minimum and then a relative maximum as we examine the magnitude of k between s equal minus 1 and s equal minus 10. And that's actually the distinction between those two patterns. If we can now determine whether or not, if k monotonically increases between minus 10 to minus 1, then we have pattern on the left, or pattern A. If we look at k as a function of s, and if we look now at k between minus 1 and minus 10 in terms of s values, and it has then a relative minimum and then a relative maximum between those, then we actually have the root locus pattern on the right, or pattern number B. So now let's determine which root locus pattern we actually have. I'm now answering the question, which magnitude of the gain k pattern do we have for this first transfer function g sub 1 of s? To determine that, let's go ahead and plot the magnitude of k between s equal minus 1 and s equal minus 10. Here we have the magnitude condition, which is k, s plus 1 over s minus 2, s plus 10, equaling 1. That's our magnitude condition. We can solve that for k, and we now have this product of our pole lengths to whatever s value we're interested in, and here we're interested in evaluating this at s values between minus 10 and minus 1, all divided by this factor s plus 1. Let me sketch that expression for k functionally with the calculator. And you can do this many different ways, but if you have a calculator, maybe you can plug this expression for k into it and then see if k is monotonically increasing, or in fact if it is experiencing some relative mins and maxes between s equal minus 1 and s equal minus 10. So what I want to do is get into the graphing mode and actually plug in the magnitude of k expression. the TI Inspire, you're now looking at, maybe if you've just opened up a graphing window, it might give you this display f1 of x. It's expecting your independent variable to be x. I'm going to now say x times x minus 2 times x plus 10 divided by x plus 1. And now the only thing I have to worry about is probably adjusting the window to display what I want. And I'm actually wanting to look at this expression. Your calculator is going to probably give you that expression for an unlimited range of x values. We just want to focus on that expression between s equal minus 10 and s, or x in this case, equal to minus 1. And y min, we really don't know what we have just yet, so let's just maybe use some numbers and see. We know that at minus 1 it's going to go off to infinity, so hopefully we can sort of see, if we set our window equal to 200, whether or not that's going to be sufficient. Let me now see if I can open up a window that has the calculator in it, and now I have my f1 of x. I want to, and conveniently enough, I've already found the absolute value function. Now I want to say x times x minus 2 times x plus 10. Whoops, let me put that in. Divided by x plus 1. And now it's giving me all sorts of ranges. So let me open up another window, which in this case, hopefully I can do that with the menu command, and I can say, okay, go to the fourth option, which is the window. Let me go to 1, which is the window settings. My minimum for x is fine, so let me tab down to x max, and I wanted that to be minus 1. Then my y value, I'm not going to be anything negative. If I want to see something there, I could, minus 1 or something. I'm just going to say 0. And here, let me go ahead and say what I said before, maybe 200. And now I can see, and there is my graph of k. This is not my root locus. This is simply the magnitude of k between minus 10 and minus 1. And you can see that there's no maximum or minimum relative in that particular sketch of the magnitude of gain k. So this is telling me that it's actually monotonically increasing the gain k from minus 10 to minus 1, which allows us to conclude that we actually have a root locus that's root locus pattern A. We do not re-enter and break away subsequently between s equal minus 1 and minus 10. We now have a pattern determined by pattern A. In our case, we now have the 2 poles and a 0, and then another pole. We had a centroid at minus 3.5, and it was at plus and minus 90 degrees. The branch at minus 10 now just merrily steps or approaches the 0, the finite 0 at minus 1, and these other branches depart from somewhere in the right half plane, and we could actually find that if we wanted to. We could go back and say, you know what, let me open up another sort of picture of this, or change the window. So if I now go to the window and say change the settings, and if I now say let's look at this value of k between 0 and 2, and my y is probably not going to be as big as it was before. Let's just say that maybe it's between 10, and now this is what's happening in the right half plane between s equals 0 and s equal 2 relative to the magnitude of k. I can actually now, that's not what I wanted to do. Let me go back over to the menu and do an analyze graph, and let me find the maximum. Now it's asking me where's the lower bound. That's fine on that particular, whoops, shouldn't have hit that key. So my lower bound there is fine. Let me just say that's fine. Now I need to scroll over, and let's say my maximum I want to be between those limits, and now it finds a maximum at 0.77, so I'm breaking away between 0.7 or at 0.78 with a k value of 5.76. So if I go back to my diagram, this breakaway point is actually occurring at s equal to 0.778, and that occurs at k equal to 5 point whatever that was, 5.76. So if I needed to know what's the gain, and you could locate that crossover frequency, I'm not going to do that, but you could do that with the Ruth array or some other technique that you want. Let's now just verify using MATLAB that in fact we have identified the correct root locus pattern. Let me enter in, and you don't have to do it in this way or fashion, but I'm going to enter in the numerator, which was s plus 1. So there's my numerator of my transfer function. My denominator I'll call d1, and just for fun, let me show you that you could convolve two different polynomials. In this case, I have a polynomial of s squared minus 2s plus 0, and I have another linear factor associated with the pole at minus 10, and I could say what are the roots of d1 just to verify that those are where I want them to be. I have a pole at 0, I have a pole at minus 10, and I have a pole at plus 2. That looks good. I can now define my transfer function as numerator and denominator. If I wanted to, I could say, let me verify where those are. I have a finite 0 at minus 1, and I have the poles, open loop poles, where I said the root locus command. I almost hesitate to show you how easy this is. You just have to say r locus of the object that you've defined as your system, in this case G1, and at some point the computer will hopefully sketch the root locus. This is now the root locus, and in fact that is consistent with what we said it was going to be for this particular system. Let's now compare that with another transfer function that might produce the other pattern, pattern B, or the pattern on the right. Let's now compare the root locus of G1 of S with G sub 2 of S, where now G sub 2 of S is S plus 1 S, S minus 2, S plus 18. The only thing that differs between G1 and G2 is that third pole that's now further into the left half plane. Again, we can sketch these, and let me just do it in, again, a linear fashion. Rule 1, we have 1, 0. That 0 is at S equal minus 1. We have 3 poles. We have a pole at the origin. We have a pole in the right half plane. This is an open loop pole at plus 2, and we have another pole at minus 18. Rule 2 now will allow us to identify the real line segments that belong on our root locus. And that is actually a pattern that's consistent with what we've already seen. Now with Rule 3, our pole zero excess is the same. It's 2. Our asymptote angles are the same. They are at 180 divided by 2 times 1 and times 3, as we let L go from 0 to 1, or they're at 90 degrees and 270 degrees, or, again, phi sub A is plus and minus 90 degrees. What has changed is the centroid. We have a pole at plus 2, a pole at the origin, and now we have a pole at minus 18. We subtract the 0 at minus 1, and we divide by the pole 0 excess, which is 2, which is 3 minus 1. So we now have minus 16 plus 1 over 2, or minus 15 over 2, or minus 7.5. And now we have a picture that looks similar to what we have already drawn for the earlier pattern. It's just now this pole, the third pole, over there in the left half plane is a little bit further away than it was in the previous system. And because of that, our asymptotes are centered now at minus 7.5, which is a little further into the left half plane. Whoops. Been calling that phi, so let's call that phi sub A of 90 degrees and minus 90 degrees. We can now look at rule number 4 to determine the breakaway and reentry points. And again, let's now plot K versus S, and I hope it's clear that we still expect a breakaway between S equals 0 and S equal plus 2. What we don't know is whether or not we have reentry and breakaway points between the 0 at minus 1 and the pole at S equal minus 18. From the magnitude condition, we get K is the three poles lengths, and we can now sketch that with our calculator, for example. Let's see now if we can go ahead and maybe put in a new that's not what I wanted to do. Let me escape out of that. Let me now actually, I'm trying to put a new window, and now I think what I want is I want a new page. So let me do Control plus page, and I want to now add a graph. So now I'm on the second graph, just so I don't mix up my graphs, and my f sub 2 is again going to be the absolute value of x times x minus 2 times x plus 18 now, divided by x plus 1, and I hope that that's what I needed. Now I can go to the window and do, so that's number 4, and window settings. Let me go ahead and just make sure my breakaway is between 0 and 2. And it looks like that is giving me what I wanted. Let me go ahead and make my window a little bit, have a y value a little bit larger than what I entered there. And I can now find an analyze graph. My lower bound I want to be right here, and my upper bound I want to be there, and there's my maximum. It's close to where it was before. It's at 0.757 and at 10. Let me go ahead and do another. I don't want to do that. So now that's my breakaway between those two. So I now have a breakaway for k equaling 10. And now let's change the window, going to the menu, doing the analyze graph, doing, whoops, not analyzing graph, escape out of there, go to number 4, which is the window, do the settings. Now I want to go for x min of minus 10, x max of minus 1, and now my y value is going to be a little bit bigger, so let me go ahead and say up to 200. Oh, I need to go back because my pole here was at minus 18, wasn't it? So now let me say that that now needs to be minus 18, and now I can say okay, and that looks a little bit better. What if you look now, you can see that I have probably a relative maximum here and a relative minimum right there to the left of minus 1, and a relative maximum a little bit to the left of that. So if I now come back to the menu and say, let me analyze that graph, let me find my minimum. The lower bound, let me say, is there. My upper bound is there. I now have a minimum right there with a gain of 112. Let me now find, analyzing graph, a maximum let me say that my lower bound for searching for that maximum is here, and my upper bound is right there. And now I have a relative maximum to the left of that point. And if I now copy that down, I have a re-entry at a value of s equal to minus 3.54 at a gain k quite a bit bigger than 10. Whoops, it's 112. I continue to crank up my gain a little bit, and I move my poles around the branches. These again are the closed loop poles, and when I get to s equal to minus 6.72 with a gain of 116, I now have another breakaway. This now allows me to more effectively at least label. I don't know if my sketch is going to be that much nicer, but I can now say that I have a better feel for where these features actually belong. My centroid of my asymptote was at minus 7.5. I had a breakaway at 0.76. I had a re-entry at minus, let's say minus 3.54. And then pretty close to this centroid, I had a breakaway at s equal to minus 6.72 was a breakaway. Meaning, I now know that as I increase the gain, and this gain at 0.76 was a gain of 10, I now, at 0.76, I break away from the real line. I then move around from that breakaway and re-enter. That should be symmetric, both above and below. I re-enter the real line at minus 3.54. One branch goes towards the finite zero at minus 1. The other one leaves and goes to the left. The one coming in from the right now collides with the one going to the left, and these now move off and approach the asymptote as k gets bigger. I could now actually verify that with MATLAB if I wanted to. Maybe you don't want to, but I sort of would like to. The numerator I didn't change, so now let me change my denominator. Let's say this is D2. This is now 1, 16, minus 36, and 0. That is coming to us because of, here was my G sub 2 of S. That was S minus 2, and S plus 18. This now becomes S squared minus 2 plus 18, or plus 16S minus 36, and then when I hit it again with the S, I have S cubed plus 16S squared minus 36S plus 0, and that's where that last coefficient becomes, and that's now my denominator polynomial, S cubed plus 16S squared minus 36S plus 0. I can now create the second system with the original numerator, the new denominator, I I can now, let me go ahead and open up a new window to plot that in and say root locus G2. And now you can see that in fact we have validated our root locus pattern. This is now the pattern on the right, or pattern B, and we now do know why that's true because of K having a relative minimum at minus 3.54 and then a relative maximum where it now breaks away at minus 6.72, and that's consistent with this particular sketch. The numerator again was just s plus 1, but this is now the picture in the complex S-plane that we've now verified or validated in MATLAB. Hopefully this was helpful in using rule number 4 to determine which pattern you had for a root locus.